Hi everybody, this is video 3 of our mini unit on colorimetry and spectrophotometry and light. And in this video, we are going to talk about the color wheel and complementary colors and how spectrophotometry takes advantage of that. So when we're talking about our visible light, remember that we can put our visible light into this color wheel. And we call these opposite colors complementary. Now, these complementary colors, that's an E, like complete, because they are the colors that complete each other. These complementary colors combine to form white light. And so any color that we see is the complement of the color of light absorbed, and it completes the color. So remember, the color that we see is what is reflected, and what is absorbed would be the complementary color. So colorimetry and spectrophotometry make use of either the human eye or instruments to make measurements of how deep the color is for a sample. And since the deepness of the color or the darkness of the color will be based on how concentrated that colorful compound is, we can see how much light it absorbs and reflects, and that will allow us to know something about its relative concentration. So just a real quick thing here for our complementary colors in your packet. Of course, this is black and white, but these would be the colors that you would use to complete or complement the colors of compounds. If you have a green compound, it's going to absorb red. If you have a blue-green, it'll absorb orange. Violet will absorb yellow, and so on. So basically, we want to use the complementary color when trying to analyze a colorful sample. Now, again, just a note, we can only use this for samples that show color. Any sample that is clear and colorless will not absorb any of this colorful light and cannot be analyzed in this way. We're going to use the process of spectrophotometry, which uses a spectrophotometer, which is that instrument that measures the amount of light absorbed or the intensity of color at a given wavelength. The intensity of color can be given a numerical value by comparing the amount of light prior to passing it through the sample and after passing it through the sample. So basically, what we have is a device that gives off a known intensity of light with a known wavelength. We pass it through our sample, and then there is some sort of detector on the other side. And the detector sees how much light is left over. So the amount of light that gets to the detector, whatever doesn't get to the detector, was absorbed by the sample. Okay, and so what is absorbed through by the sample is called absorbance. What gets to the detector is called transmittance. That is the light that is transmitted to the sample. I'm sorry, to the detector. We have this equation for transmittance for our purposes. We don't need to worry about that. Transmittance and absorbance for the devices that we have are done by the digital devices. Okay. The one piece that we do have to be focused on, though, is this Beer's law or Beer-Lambert law, which tells us that there is a linear relationship between absorbance of light and the concentration of the sample. And this is A equals epsilon BC, where A is absorbance, epsilon is the absorptivity constant, B is the path length, and C is the concentration of the sample. And the way that we're going to do this, again, light is going to pass through the sample, and the lower the concentration, the less light the sample will absorb. The higher the concentration, the more light the sample will absorb. And we can do what's called a working curve, where we use samples of known concentration and we plot their concentrations versus absorbance, and we should get this working curve so that then if we analyze another sample and we find out its absorbance, we find it on the line, and then we can find its concentration from this line of best fit. So now the simple scheme of this spectrophotometer is that we have a sample in a cuvette, which is a fancy name pretty much for the test tube that we put in. And this cuvette is made of very, very clear and very high, very glass or plastic with very high clarity so that it doesn't block the light. There is a lamp and a lens that causes the light to go and become in a specific wavelength. This wavelength is the one that should be set to the complementary color of the sample. So again, if we look back at the color wheel, if it's a blue sample, okay, a blue sample should have orange light going through it. So again, here we go. Sorry for making you dizzy. This sample is blue. We're going to monochromate this and we're going to turn that light so that it is orange light coming through the sample. The sample will absorb the best in the orange wavelength because orange is the complementary color to blue, and whatever light does not get absorbed by the sample will reach the detector. Once the algorithm that the machine has to use is complete, the detector will give us an absorbance value. This absorbance value can then be put onto our concentration graph versus absorbance, and we can plot, oh, the absorbance was here, so the concentration must be, 3 milligrams per milliliter or something like that. The other thing we can do is if we have our molar absorptivity constant and we know the path length, we can put the absorbance in and find the concentration. This is a picture of an older Spectronic 20. We will be talking more about this when we get to chapter 12 because we do a lab where we do absorbance for concentration in kinetics. But this is just a picture. We do have one of these of an old Spec 20. Now, once we put the sample in that we are going to calibrate the Spectronic 20 in, we actually can plot wavelength versus absorbance for a very concentrated solution, and we will get a peak absorbance at a specific value. That peak, where the solution absorbs the most light possible, that will be the complementary color for the solution. So notice for red, the complementary color is at about 525, whereas for blue, the complementary color is at about 625. Red and blue have two different complementary colors. That is going to end our presentation for the Beer's Law and the Spec 20 and the colorimetry. So just a little recap for our Beer's Law. A equals epsilon BC, which means that our absorbance is equal to the molar absorptivity constant times the path length. And remember that the distance that's in the constant unit has to match the distance unit in the path length. And then C would be the concentration in molarity. We also know that if we're analyzing something based on Beer's law, the solution has to be colorful. And we are, oops, I didn't even spell that right, huh? Colorful, sorry about that. And we have to use light that is set to the wavelength of the complementary color for best results. So this may seem a little bit out there still based on the Beer's law, but at this point, the next piece that you should do to complete this Beer's law information and to illustrate much better what we're talking about in this is do the Beer's law PhET simulation. For my students, you have that attached to your notes packet. And if you work on that Beer's Law PhET and then go back through this video, that should be something that would be really helpful. So as always, if you have any questions, first thing while you're watching a flipped video, you can always pause, rewind, and go back. So if you had something that you wanted to go back over, you can certainly go back to that point in the video and replay it. But absolutely, please ask me questions in class or an extra help if anything in here was not clear to you. Have a good day.